in this problem you have two trains and let us call them A and B. So this is train A, and on the same track you have another train which is called B. Now train A is moving in the rightward direction at a velocity of 25 meters per second, and train B is moving in the leftward direction at a velocity of 35 meters per second. When the distance between the two trains is 1000 meters, each driver sees the other's train and he applies the brakes, and this results in an acceleration of minus 1 meter per second square for train A, and similarly minus 1 meter per second square for train B. Just to clarify, this 25 meters per second and minus 1 meter per second are the velocity and acceleration respectively in this direction for train A, whereas for train B 35 meter per second and minus 1 meter per second square are the velocity and acceleration respectively in this direction. Now to find out whether the collision is avoided or not in the ground frame is a very easy procedure. What we do is to analyze the motion of train A assuming that train B is absent. In other words, I'll draw train A over here. It's moving towards the right at 25 meters per second and its acceleration is minus 1 meter per second square. Now what I do is to find the displacement of train A, which I call SA, in the rightward direction. I can do it by the normal formulae for UALM. Similarly, I find the displacement of train B in the leftward direction assuming that train A is absent. Now if the sum of SA and SB is larger than the current distance or the initial distance between the two trains, which is 1000 meters, then obviously it would mean that train A and train B must either pass through each other, which of course is not possible, and so it means that there is a collision. On the other hand, if SA plus SB is less than 1000 meters, then the trains stop short of each other and the collision is avoided. The third case is of course with an equal sign, that is SA plus SB is equal to 1000 meters, which would mean that the trains just touch each other when they both stop. So accordingly, let us analyze the motion of train A in the ground frame. What I do is I apply V square is equal to U square plus twice AS, and of course I remember that the positive direction which I have chosen for train A is given by this arrow. Now remember, train B is assumed to be absent, so train A finally it must stop at some point of time, and the final velocity therefore I will take as 0. So 0 square is equal to, the initial velocity is 25 square, 25 meter per second the whole square, plus 2 multiplied by the acceleration of train A in the rightward direction is minus 1 meter per second square, and the displacement of train A in the rightward direction by the time it stops is given by SA. Now if you just manipulate this equation, finally you get a value of SA equal to 625 divided by 2 meters. In other words, train A in the absence of train B would stop after traveling 625 by 2 meters in the rightward direction. Now let us likewise analyze the situation for train B. Let's assume that train A was absent and train B is being viewed from the ground. We know that train B's initial velocity in the leftward direction is 35 meters per second, and once the brakes are applied the acceleration is minus 1 meter per second square, once again in the leftward direction. So in the leftward direction we apply the equation v square is equal to u square plus twice as to train B. Remember, this time the leftward direction is treated as positive. When train B finally stops, which it must at some point of time, V is equal to 0. So I have 0 square equals 35 meter per second the whole square plus 2 multiplied by minus 1 meter per second square multiplied by, now the displacement which train B undergoes in the leftward direction by the time it stops, I call it SB, and by manipulating this equation one can find SB to be equal to 1225 divided by 2 meters, which would mean that in the absence of train A, train B would travel 1225 upon 2 meters in the leftward direction by the time it stops. And finally, to check whether the collision is avoided, we add SA and SB. So when you do that, SA plus SB turns out to be 925 meters. And since 925 meters is less than the initial distance between the two trains, which was 1000 meters, clearly the collision is avoided, and the picture can be summed up as follows. The initial separation between the two trains is 1000 meters. Train A is traveling towards the right and train B is traveling towards the left. Now train A stops after a rightward displacement of 625 by 2, which is 312.5 meters. So train A will stop roughly around here. That's train A which has stopped, and this distance is 312.5 meters. On the other hand, train B stops after traveling left a distance of 1225 upon 2 meters, which is 612.5 meters. So train B would stop somewhere over here. That's train B which has stopped, and this distance is 612.5 meters. And we have calculated earlier that the sum of these two numbers, that is 312.5 meters and 612.5 meters, that's the sum of the two displacements, is 925 meters, which would mean that the intervening distance between the trains, the distance that remains between the two trains when they stop, is 1000 minus 925 meters, which is of course 75 meters. In other words, if we analyze the situation from the ground frame, the collision is definitely avoided, and by the time the two trains stop, the distance between them is 75 meters. In the next part of the question, that is part B, we have to redo the problem by using relative motion techniques, and in particular the problem has to be analyzed in the reference frame of the second train. So to start with, I will redraw the diagram in the ground frame, and as you can see, the initial distance between the two trains is 1000 meters. Train A is traveling rightward at an initial velocity of 25 meters per second and an acceleration of minus 1 meter per second square. Both the velocity and the acceleration are measured with respect to the rightward arrow. Similarly, train B is traveling in the leftward direction, and with respect to this particular leftward arrow, the initial velocity of train B is 35 meters per second and its acceleration is minus 1 meter per second square. Now we have to redraw the diagram by attaching a reference frame to train B and calculating all of these physical quantities in this particular reference frame, namely the reference frame of B. So this is what we have done over here in the second diagram. Now in a reference frame which is attached to B, B will constantly be at rest. So that's what I'll write over here. That is, B's velocity is always equal to 0 and its acceleration is also always equal to 0. Now let's try and find the corresponding velocity and acceleration for train A. Now let's look at the velocity first. In the ground frame, A's velocity is 25 meters per second rightward. This particular number I've written over here. So A's velocity is 25 meters per second in the rightward direction. That's V A bar. And B's velocity is this number over here. So I'll write VB bar is 35 meters per second in the leftward direction. Now clearly the velocity of A in B's reference frame, which is of course denoted by V bar A comma B, that's given by VA bar minus VB bar. So that's going to be 25 rightward, 25 meters per second rightward, minus 35 meters per second in the leftward direction. Now what I can do is this minus 35 in the leftward direction, I can change it to plus 35 in the rightward direction, and when I add these, what I get is 60 meters per second in the rightward direction. This means that in this diagram, train A is traveling rightward at a velocity of 60 meters per second, where the velocity is measured in a reference frame attached to B. In a similar manner, let us now evaluate the acceleration of A with respect to B. It's a force given by the acceleration of A measured in the ground frame minus the acceleration of B in the ground frame, which is going to be the acceleration of A in the ground frame is of course this. So I'll write minus 1 meter per second square in the rightward direction minus the acceleration of B in the ground frame is given by this. So it's going to be minus 1 meter per second square in the leftward direction. And once again, this minus sign can be changed to a plus sign, provided that this leftward pointing arrow, I make it rightward pointing. So what I've got is two vectors of minus 1 meter per second square. Both of them are in the rightward direction, and so when I add them, I get minus 2 meters per second square in the rightward direction. Now I can return to my diagram, wherein I can write the acceleration of A as measured in B's frame as minus 2 meters per second square in the rightward direction. As mentioned in the question, we have to attempt to solve the problem in B's reference frame, and so we will now concentrate on the lower diagram. B in this reference frame is always at rest, and since in this reference frame A has an initial velocity of 60 meters per second rightward and an acceleration of minus 2 meter per second square rightward, A's velocity would decrease with respect to time, whereas B would permanently be at rest, and it would therefore appear that we merely have to find the displacement of A in this, that is in B's reference frame. And for example, if A's rightward displacement is less than 1000 meter, it would mean that A stops short of B and the collision is avoided. On the other hand, if A's rightward displacement as measured by B, that is as measured in B's frame, is greater than 1000 meter, it would mean that A would stop over here in the absence of B, and hence the collision would actually take place. So the whole question now revolves upon the answer of this particular question: is the displacement of A as measured in B's reference frame less than 1000 meters? If the answer is yes, it appears that the collision is avoided. Now, sticking to this particular reference frame, that is B's reference frame, let me apply the equation V square is equal to U square plus twice AS to train A. Remember, we have taken rightward as positive, and all these vectors are measured in B's reference frame. Now the final velocity of A I'll put as 0, and the initial velocity of train A is 60 meters per second, so 60 square plus 2 multiplied by the acceleration of A in B's frame is minus 2 meter per second square, and S would of course be the displacement of A with respect to B. Now when we solve this particular equation for SA comma B, we get an answer of 900 meters. Now if you look at this answer, it is clearly smaller than 1000 meters. It does appear that if we analyze the situation in B's frame rather than from the ground frame, the collision still seems to be avoided. However, the final distance between train A and B using this method would be the initial distance, which is 1000 meters, minus the displacement of train A in the rightward direction, which is 900 meters, and that would leave a distance of 100 meters between A and B. In short, by this method, it appears that we have concluded that the train A and B will not collide. However, unlike in the previous method, the final distance between the two trains is now 100 meters, whereas in the previous method with respect to the ground, that is, the final distance turned out to be 75 meters. Now this is a surprising result because, as we know, distance or length is absolute in Newtonian mechanics or in classical mechanics. We simply cannot have a situation in classical mechanics where the distance between two trains A and B is different as measured by two different observers at the same time. Clearly, at least one of these methods seems to be wrong. Which of these two methods is correct and which of them is wrong is the subject matter of the third sub-question, in which we are asked to explain this discrepancy, that is, the difference in the distances, the final distances between the two trains as calculated by the two methods. We will now resolve this rather surprising situation by showing that we have gone wrong in the second method, and the place where we have gone wrong is by making an assumption that the acceleration of train A with respect to train B is constantly minus 2 meters per second square throughout the process. Now let's make a small calculation and find out how long the entire process lasts according to this particular assumption. Now that calculation is very easy. We simply apply the equation V equals U plus AT in the second diagram, that is, in the diagram drawn with respect to B. You apply this equation to train A. The final velocity of train A with respect to B is equal to 0. That's when the process stops. The initial velocity is 60 meters per second. The acceleration is minus 2 meters per second square, and the time taken for the process is t. So clearly the value of t is going to be 30 seconds. Now this would mean that under this particular assumption, that is, the acceleration of train A is minus 2 meters per second square throughout the process lasts for a total time interval of 30 seconds, and after the end of the process both trains are at rest relative to each other, and since the two trains have traveled a total distance of 900 meters, the final distance between them is going to be 1000 minus 900, which is of course 100 meters. So just for our reference, I'm going to write over here the total time required for the process is 30 seconds, and also the final distance between the two trains when the process ends is equal to 100 meters. To find out where we have gone wrong, we first ask ourselves the question, looking at the diagram which has been drawn with respect to the ground, can we make out whether both trains are going to stop simultaneously or whether one train stops earlier than the other train? Clearly, if we treat this particular diagram to be drawn at t equal to 0, then we can apply v is equal to u plus at to train A in the ground frame, and we can get 0 equals 25 plus minus 1 multiplied by the time at which train A stops, and we get TA is equal to 25 seconds. So train A would stop at a time equal to 25 seconds. Similarly, if I apply v is equal to u plus at to train B to find out when it stops, v you put it as 0, u is 35 meters per second. Remember, leftward is positive now for train B, that is, plus the acceleration of train B is minus 1 meter per second square, and multiplied by the time tb at which train B stops. Solving this equation, we get tb is 35 seconds. Now clearly this means that train A and train B do not stop simultaneously. It is train A which stops first, and after it stops, train B still continues traveling for 10 more seconds. After that, of course, train B2 stops, and that is the time when the process finally ends. Now what that means is that when I draw the diagram with respect to the ground, the acceleration of train A is minus 1 meter per second square, and that of B is minus 1 meter per second square. But this situation prevails only for the first 25 seconds of the motion, that is, from t equal to 0 to t equal to 25 seconds. Now at t equal to 25 seconds, train A stops. So its acceleration, the acceleration of train A, becomes 0 meters per second square at t equal to 25 seconds and also thereafter. Remember, when train A stops, it's going to stop permanently. It's not going to travel in the backward direction, which would have happened if its acceleration was always equal to minus 1 meter per second square. Here, the acceleration is minus 1 meter per second square, that is because of the train braking. But once the train A stops, the train A is not going to travel in the backward direction, and hence the acceleration after t equal to 25 seconds of train A is equal to 0. Of course, we do know that after t is equal to 25 seconds and right up to t equal to 35 seconds, train B is still moving with respect to the ground, and its acceleration during this particular time interval is still minus 1 meter per second square, that is, with respect to the ground. Now what this means is that when I draw the picture with respect to train B, I get two different diagrams. One diagram is for the time interval from 0 to 25 seconds, during which, with respect to train B is itself at rest, of course, and train A travels at an acceleration of minus 2 meters per second square, which is got, of course, by subtracting B's acceleration from A's acceleration, taking the values which prevail for the first 25 seconds. On the other hand, if we draw the diagram once again with respect to train B, but for the next 10 seconds, that is, for t greater than 25 seconds and less than or equal to 35 seconds, train B, of course, is going to be at rest because the reference frame is attached to B. But train A is going to move with respect to train B with an acceleration of minus 1 meter per second square, which is got by subtracting B's acceleration from A's acceleration in the ground frame, taking the values which prevail from t greater than 25 seconds right up to t equal to 35 seconds. Now what this means is that our assumption that A's acceleration with respect to B was minus 2 meters per second square throughout the process was wrong. Notice that under that assumption, the process lasted for a total time of 30 seconds, whereas in reality, for the first 25 seconds of the process, the acceleration of A with respect to B is no doubt equal to minus 2 meters per second square, but thereafter it's not minus 2 but minus 1 meter per second square. And so naturally we cannot expect these two answers which we obtained under wrong assumptions to be correct. In fact, since A's acceleration in the reference frame of B does not continuously remain at a level of minus 2 meters per second square, but it is rather minus 2 meters per second square for the first 25 seconds of the process, and thereafter it is minus 1 meter per second square. It also means that A's deceleration with respect to B is not 2 meters per second square throughout the process, but rather it is 2 meters per second square for the first 25 seconds, and thereafter it is 1 meter per second square. It means that we have overestimated the deceleration of A with respect to B in this earlier method. And since our estimate of deceleration is an overestimate, naturally train A will come to rest with respect to B at some time which is greater than 30 seconds, which in fact we know to be t equal to 35 seconds from the very first method which we did with respect to the ground. And also we know that since the deceleration has been overestimated, train A will actually come to rest with respect to B after covering a larger relative distance, and hence the final distance between train A and B will be smaller than 100 meters. And of course we do know that the actual final distance between the two trains will be 75 meters from the first method that we did, that is in the ground frame.